Professor Shubhan, can you hear me?
Yeah, you can
So I
start.
think it's 6 o'clock. We can start, right?
Yeah, sure.
Yeah. So good evening, everyone, and welcome to the fifth session of our colloquium, online colloquium session. And before I start, I'll briefly tell about LNMIIT, especially for those who joined externally or not our own students or faculty members. That we have a small physics department of quite a few good faculty members, and this institute LNMIIT started its journey at 2002, and the physics department was formally established on 2012. And currently, we have, along with teaching BTech students, we also have our own MSc program and PhD program, which is quite vibrant, and there are quite a few students there. And any of you, if you are interested to join any of the program, can contact us, or otherwise for any academic collaboration, or otherwise if you just want to see our campus, beautiful campus, small and beautiful campus, you can also contact us, and you are welcome to all of you are welcome to our campus. Now it's my pleasure to introduce our distinguished speaker, whom I knew personally at some point and then lost contact for several years. We just remained Facebook friend for quite some time, and he's none other than Professor Anirban Chakraborty. And he works roughly, in my understanding, at the crossroad of physics, mathematics, statistics, and now it's AI and data science. And what he does is broadly can be described as complex system, and it has applications in physical system, biological system, financial markets, now big data and AI. So Professor Chakraborty is a professor at School of Computational and Integrative Science at JNU, New Delhi. So his academic journey, I think, started with a master in physics from University of Calcutta, PhD from Shah Institute of Nuclear Physics, and then he has prestigious habilitation from University Pierre at Marie Curie in Paris. And he's working more than 2 decades, and he also held quite a few academic and administrative roles at various universities, like being registered at JNU, associate professor at École Centrale Paris, and dean of engineering at BML Manjula, and so on. So, with this small introduction, I invite Professor Chakraborty for this talk, and I think with this talk, we can see some hidden pattern or shape of data, which is not limited to so-called data science, or it is more than data science or more than physical science. I think he will put everything in a broader perspective. So I welcome Professor Chakraborty for his presentation.
Thank you, Dr. Nupindu and Professor Shubhan for inviting me to give this colloquium. And of course, as he has rightly said, I'll be covering a huge spectrum of topics, actually. And so you can just sit back and relax. There won't be too many technical details, but I'll try to give you an overview, because the whole way of thinking you'll see that is a different way of doing science. And so I'll go very slowly, try to explain the philosophy of science, the approach that we are following, and then go to different applications. So as I have put the title, Can We See the Shape of Data? And as Upendu pointed out, I will be actually talking about, just a second. Share. It's not moving.
I think we can't see any slides.
Right, I'll just share it once more.
Please take your time.
Can you see now?
Not yet. Yeah, now we can see.
So I will be covering different topics. Like on the left, you see sort of 70,000 starlings making some ordered motion. Then you'll see a traffic system where, if you have a disorder, then we call it a traffic jam. Then you have a movement of market where the stock prices are moving up and down. And finally, on the right, the snippet shows the environmental system, so Arctic sea ice melting and things like that. Now, this title which I've given was inspired from a paper written by Mark Katz. He's a famous mathematical physicist, and he contributed largely to nonlinear dynamics and also in stochastic partial differential equations. So you can see that he wrote a paper called way back in 1966. And it was very interesting that he actually told that the frequencies at which the drum head can vibrate depends on its shapes. And we typically solve the Helmholtz equation to look at those frequencies. And the frequencies are basically the eigenvalues of the Laplacian. And so he said that if I know two shapes which yield the same set of frequencies, can I, starting from the frequencies, determine the shape of the drum? And the answer came out to be negative. It took almost 30, 40 years for people to prove rigorously that the answer is no. So if you want to check, you can look at this Wikipedia entry, Hearing the Shape of a Drum. Though I've taken the title from there, I will be talking on a very different scale. And so I wanted to start by giving my background and sharing my experiences as a student and a scholar. So I was born in a very small town called Darjeeling. I don't know how many of you have visited. So you'll see the third highest mountain in the world, Mount Kanchenjunga. The tip is here. And this photo was taken by one of my classmates, actually. And you can see very clear sky in the background, no pollution, unlike in Delhi, where I am currently. So these stars used to remind me of these rhyme, Twinkle, twinkle, little star, how I wonder what you are. I'm sure everybody's familiar with this nursery rhyme. But what I wanted to point out are these three italicized words: wonder, how, and what. So what we do is we start wondering and asking the questions how and what. And that's how I ended up being a scientist. And I still keep wondering and asking the questions how and what. So I did my class 10th from the school called St. Joseph's. It was established by the Catholic Brothers way back in 1888. And it's a very old school. Then I went to what we call the Mount Hermon School, that's under the Protestant Church, and again, a very old school established in 1895. Then I came for my bachelor's to Scottish Church College in Kolkata. That was established in 1830. Second oldest college after presidency in Kolkata. And for my master's and PhD from Shah Institute of Nuclear Physics. Then my journey continued as a postdoc at Helsinki University of Technology. And there, in fact, I survived temperatures of minus 39 degrees Celsius. Then I moved to Brookhaven National Lab, which is very famous for its particle accelerators. So you can see the relativistic heavy ion collider at the background, and this is the NSLS light source. And then I went to Banaras Hindu University, which is one of the largest universities in Asia. And here, in fact, I survived temperatures of plus 48 degrees Celsius. So anything between minus 39 and plus 48, I'm happy, actually. So then I was offered a permanent position at École Centrale Paris, and it's one of these, what we call Grande École in French. That means a specialized school, specialized engineering school. And I spent 5 years, and then I returned to India as a professor at the Jawaharlal Nehru University. at the School of Computational Integrative Science. So that's been roughly my academic and professional career. On the left, you will see that I have my scholars, my PhD scholars. Most of the work I will be covering today are done by them, and some of my master's students who are on the right. So I give my acknowledgement to them. And of course, for the support throughout my career, my wife and my kids. So I wanted to thank them also. If they don't allow me to spare this time outside working hours, then I wouldn't be able to give this lecture. So in this thing, I of course have a lot of collaborators. I could not put the names of all of them, but you'll also see that they're very interdisciplinary. So Dr. Shorish and Dr. Shubho are statisticians. Dr. Sudeep is an environmental scientist. And then Professor Seligman is a physicist. Onindo is an economist. And these are my former scholars, Alka and Kiran and Hirdesh. And current scholars, Ashok, Rishi, Abhinav did his internship with me and is currently doing his master's at UCL. Manya and Sejal are currently working as interns. And Anish is a postdoc currently at CMI. So I wanted to start with very basic question. Of course, all of you who are attending know what is science, but I wanted to remind that the science itself is a area of knowledge which covers sort of general truths or the operations of general laws, especially as obtained and tested through scientific method. So then your natural question could be, what is a scientific method? And I have a cartoon here which tells you that, okay, here what is described as a scientific method. So there is a child, it makes an observation, so it finds an object on the ground, it forms a hypothesis that perhaps this object is edible. So it performs the experiment, it takes the object and puts it in its mouth, and then it analyzes the data. So you can see that the color of the face has changed from cream to more greenish. That means it didn't like the taste of the object. And then because it doesn't like, it starts crying. And that's like the reporting of the findings of the experiment. And then it invites others to reproduce the results. So it invites another kid. So then you realize that there are two aspects of science which are very important and as shown in the scientific method. One is verifiability and the other one is reproducibility. So I can make a hypothesis and I can verify it. So that's the first part. The second part is it must be reproduced by others and they must come to same conclusions. So whenever you are in a dilemma, whether this is science or pseudoscience, you can test with this scientific method. And that is what was encouraged by our forefathers and people who established or wrote the Constitution of India. They wrote it in the Constitution that everybody must instill us a concept of scientific temper. And this is given in the article itself, that you should be having evidence-based approach to problems, rational thinking, critical questioning, and integrating scientific values and humanistic ideals to promote a more informed and progressive society. So as educated people, we are coming from different institutions, it is our duty to also instill the spirit of scientific temper amongst others. Then only we can progress as a nation. Now, typically, the way we do science, we call it reductionism. Okay? And so you may ask, what is reductionism? So if I ask a question, what are we made up of? And here what I do is I have a video. I'll play this video. So you see a human hand. As you have seen, we started with, what is our hand made up of? And somebody would say that, okay, it is made up of, skin, blood, and bones. And these are all different types of tissues. And then I asked the question, what are the tissues made up of? Different type of cells. What is the cell made up of? Different type of organelles like chromosomes, mitochondria, ribosomes. What is the chromosome made up of? It is made up of DNA. What is the DNA made up of? It is made up of different chemical molecules, atoms and molecules. What are the atoms made up of? They are made up of neutrons, protons in the nucleus, and the electrons surrounding them. What are the neutrons and protons made up of? They are made up of different types of quarks bound by gluons. And what are these made up of? You've already heard another colloquium by Professor Gautam Mondal, that they're made up of strings. So what we did is we reduced from a very complex object to very small elementary particles. And so you will see that this is a cartoon taken from the Fermi National Lab in US, which tells that, see, these are all the types of different particles that you have in the universe. And as we know, there are only two different types of particles. Some which are called fermions form the matter, and the other, which are the interactions or forces, are bosons. So fermions, because they obey the Fermi-Dirac statistics, and bosons because they obey the Bose-Einstein statistics. Now, if I give you this information, would it be possible to describe how the universe works? The answer is partially yes and partially no. Because you will realize that, and this was wonderfully illustrated by another article written by the Nobel laureate Phil W. Anderson. So he wrote an article called More is Different in 1972, which was published in Science. And he showed the way I described, for example, of the sciences. And we went from sort of where I was talking about biology, physiology, to cellular biology, to molecular biology, to chemistry, to many body physics and particle physics. But you will realize that every level there are new laws, new concepts, new generalizations. And so, if I am a many body physicist, there is no guarantee I will be good at chemistry. If I'm good at chemistry, I may not be good at molecular biology, and so forth and so on. And so, often you also need a bottoms up approach or an integrative approach, which we call the science, complexity science approach. And so you will see that I have a cartoon sort of which tells, what I was describing, that, the psychologists here are teasing the sociologists that sociology is just applied psychology. Psychology, the biologists are saying that psychology is just applied biology and so forth. And physicists are saying that, chemistry is basically applied physics. And then we have the mathematicians who said, oh, I didn't see you all. You are over there. Because they think that they're the most pure form of knowledge. Now, what is mathematics? As Galileo put in Latin, this is a rough translation, mathematics is the language with which God has written the universe. And as the physicist Nobel laureate Richard Feynman says, that mathematics is not just a language, mathematics is a language plus reasoning. It's like a language plus logic, dot, dot, dot. And so by mathematics, it is possible to connect one statement to another. So you will see that the type of research that we do, again, the sort of knitting is done by mathematics. And in the takeaway message, I will show you why I said this. So if I ask again, what is complexity science? It's basically a new field of science studying how parts of a system give rise to collective behavior of the system and how the system interacts with its environment. So systems are complex and they often have properties like nonlinearity, emergence, spontaneous ordering, adaptation, feedback loops. And the systems which I had described on the first slide many of them show a lot of these properties. You will see that there is a very interesting issue published in April 1999 in the journal Science, which deals entirely with complex systems. And if you go to Wikipedia and search that, okay, what are the types of tools and things that you use to study complex systems, you will see that all these different types are there. In my own research, I have used all these red encircled ones, and which are like, I started with collective behavior, and then game theory, nonlinear dynamics, network science, pattern formation, evolution, adaptation, and so forth. So I start by giving an example of a very simple chaotic system, which is the double pendulum. So you've all studied the simple pendulum in the 12th and maybe double pendulum in your bachelor's. So here you see that, two rods are there. And if I follow the trajectory by the end of this rod, you'll see that it does a chaotic motion. Now, this is a single. If I have 2,500 such pendulum and I arrange them in a specific order, and then what I do is I actually set them into motion from different initial conditions. And then you will see that there is a competition between order and disorder. And so physicists have been studying the edge of chaos, or like where the chaos ends and order starts. And in fact, there is a wonderful book written by the Professor Goin Farmer, who's now the director of Institute of New Economic Thinking in Oxford University. He used to be a scientist at Los Alamos National Lab in the US, and he wrote a very nice book called Making Sense of Chaos, A Better Economics for a Better World. So if you want to have a popular way of understanding how the economy works and how this interdisciplinary field can contribute towards economics, I would suggest you to read this book. Now, the same type of chaos also functions in our brain. And so this is an article from 1st September 2025, a couple of months ago, and where people are actually pointing out that gray matter lies near a tipping point between order and disorder. And this is what we call the critical zone, the edge of chaos. And this same type of phenomena happens across physical systems. So I'm sure Nupindu and all work in condensed matter physics and magnetic things, materials, where you see a transition between ferromagnetism and paramagnetism, and in phenomena like avalanche, in spread of forest fires, which we explain through population theory and other things, and similar across different systems. Now, there was another very recent article published, in September, or in fact, end of October, it was published online, that falling asleep also follows a predictable bifurcation diagram. And you have a tipping point and a critical slowing down. Now, both these words are often encountered in physics, like I was describing, also in the magnetic systems. And here they point out that, the sleep onset is like a tipping point. And we will see that similar type of thing happens in a financial market or in many other systems that we study in the environmental science. So the Nobel Prize on Physics of Complex Systems was given in 2021 to three scientists. One was Sukuro Manabe, and I'll cover some of his work in the later half, Klaus Hasselmann and Giorgio Parisi. I had the fortune of attending his lectures when I started my PhD in 1999 at ICTP Trieste, and he was giving a course on his replica symmetry breaking in disordered systems. So he actually wrote a book called In a Flight of Starlings. And as I was describing here, you see 70,000 starlings making sometimes an ordered motion, and in other times it's a disordered motion. So if you look at the birds, what they do is they only have short range interactions. And through these short range interactions, they actually form a long range ordering. So this is again a sort of a competition between order and disorder, depending on these interactions. In 24, the Nobel Prize in physics were given to Hopfield and Hinton, and we've already seen that there was a lot of controversy. And in the chemistry also, it was given to David Baker, Demis Hassabis, and John Jumper. And again, there was a lot of controversy. And so you will see that the following week after the declaration of the Nobel Prize, there was a very nice article pointed out by the journalists of New York Times, where they said that, see, when the Nobel Prize was sort of started, the idea of Alfred Nobel was that it had a very romantic view of science, that typically a lone genius would be actually working in physics or in chemistry or in medicine, and they would be solving the problems and getting the Nobel Prize. But the world's current problems, from climate change to food insecurity to cancer and extinction, do not respect these boundaries. And in fact, we have to have an interdisciplinary approach. And so new types of fields are coming up. And so a geochemist, a paleogenomicist, a computational evolutionary theorist, astrobiologist. So these are some things which we never heard about a century back. And so, what we are proposing is that you must have a more holistic and interdisciplinary approach when you try to solve problems as this. So, as this cartoon shows, this is again taken from a Buddhist parable more than 2,500 years ago, that there are six blindfolded men touching different parts of the elephant and thinking that these are different objects. But when you take away the blindfold, then you see that you are actually, all of us are touching the elephant. And we don't see that if we work in silo. So what we want to show is that you must have a more holistic approach if you want to have this type of. Now, after that controversy, there was an interview taken and published by Nature, and they said that there was a discussion that your prize-winning work was not really physics, but computer science. What do you think? And very rightly, John Hopfield remarked that my definition of physics is that physics is not what you're working on, but how you're working on it. If you have the attitude of someone who comes from physics, it's a physics problem. And I remember that in my early days of my PhD, I used to and I also have this type of criticism because I used to work in the field of econophysics. And so the physicists would say, no, 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 this is not physics, this is economics. And the economists would say, no, 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 this is not economics, this is physics. And it was very difficult to actually work and get oneself, established. Now, recently there was a very interesting article, again, the strange physics that gave birth to AI, and it's taken from Quantum magazine, where they point out the spin glasses, the physics of spin glasses actually gave this idea, and John Hopfield borrowed this idea of spin glass physics and came up with a model for artificial neural network. And so he said that the associative memory was a part of that problem, and he took the tools of condensed matter physics, which he used. Now, you will see that one of the most popular scientists, Stephen Hawking, advised the 21st century grads when he was asked, and this is taken from a blog written by Ashutosh Choglekar and published in Scientific American. So when they asked him that, what do you think would be the most important aspects of physics in the 21st century, Hawking replied that it would be the century of complexity. And two essential qualities which he advised the new college grads, and grads in the US terminology means PhD scholars, is that they should learn statistics and data visualization. And that is what we are doing now. We are using the tools of statistics and data visualization in solving problems of complex systems. Now, before I progress further, I wanted to remind you of another quote which was given by Professor Herbert Simon, who's a Nobel laureate in economics and one of the first persons to apply tools of artificial intelligence in economics. And he rightly said that perhaps the right way to move is to understand before one predicts. And so that's what we've been doing. We have been bridging the data and science. And our questions are how and what, as I started with my first slide. And so we have published a book from Cambridge University Press, UK, which is called Data Science for Complex Systems. And it's written by Onindo, who's an economist, Shubho, who is a statistician, and myself, a physicist. So you can see that this is a very interdisciplinary book. And I'm sure if you come from any of these backgrounds or any other thing, you would be able to follow this. Now, if you ask me about interdisciplinary science, I would want to point out to an article which I've written recently, Max Weber, that when he was asked by his colleagues that what is your field, he said, I'm not a donkey and I don't have a field. So that's my approach. Same with me. I say that I'm not a donkey and I don't have a field. So I work across the fields, and you can read this article. It's publicly available. Now, in the end of the article, I pointed out a quote by Edward Witten, who is one of the highest cited theoretical physicists and one of the most brilliant scientists of our times. He said that the world is complicated and you need to know a little bit about a lot of things. And so you will see that currently all the problems that we are solving, we need to collaborate and work hand in hand with scientists coming from different fields. And I would request you, if you are a physicist, to be have an open mind and collaborate with people coming from other branches. So with this, now I am actually in the field of income inequality explained by different types of kinetic exchange models. So if you search in Google something called yard sale model, you will see that this was introduced in 2002 by Anirban Chakravarti, that's me, when I was working as a PhD scholar at Shah Institute of Nuclear Physics. And then we made several other models throughout the years. And some of these have been summarized in this journal called Science and Culture. And you'll see that the cover page has something where we try to explain the model economy as a exchange of money between different agents. Now, this journal was actually started by Meghnad Saha and Acharya Prafulla Chandra Ray, and it's a very old journal. And some of the current editors include Professor Arnab Rai Chaudhary from ISC, Professor Vikas Chakravarti, and others who are all in the advisory board. And it actually tells how science can help also to the society and development of the society and building up the culture. So if you have a mobile phone, you can scan this code. You will find that it's an article pointing out to something called pudding.cool/2022 and a yard sale model. I won't explain in details. I actually prepared a video which shows that if you start, buying and selling some object, here it's a watch. And I buy it, but I realize that I have paid much more than I should have paid. And I hope that in the subsequent trades, I would actually be able to make up for the loss. And then we find out that no, that's not how things happen. So if I have a large economy where there are a lot of traders, you will find that the money goes and lands up with only a handful of people, and they are the super rich. And so it shows you that if you are in a room of 99 other people, and then we pick up any two of them and they start trading with each other, and they all start with the same amount of money, but because they are making profits and losses, and subsequently you can actually show that there will be a lot of trades. I will just skip this video, but you can actually go to the site and scroll for yourself and check out. It's like it's a website where you can scroll one, and maybe you have lost in the first round, but in several rounds, if you play, we will see that the money slowly gets accumulated with only a handful of people. And that's not something which we desire in the society, but that's how society works, and we call that an oligarchy. So you will see that somebody is actually winning, and another person keeps on losing, and it's a zero-sum game. So when money flows from my pocket to your pocket, you make a gain and I make a loss. When it flows from your pocket to my pocket, you make a loss and I gain some money. So this way, if I continue doing, you'll see that it comes to the end of the article where it points out to the paper which I had written in 2002. And this was the paper which was published in the journal called International Journal of Modern Physics in World Scientific. It talks about distributions of money in model markets. And it was called yard sale model because a journalist who published an article in American Scientist in 2002 talked about my model. and he named it yard sale model. So the name has stuck on, and you can find a very good article written in the Scientific American by a professor of mathematics in the US. His name is Bruce Boghossian, where they explain what I was telling, that how these asymmetric trades land up. So some people land up with a huge amount of money, and the others do not have any money left. So you will see that this type of inequality happens in every society. Now, this is a cartoon which shows the 17 UN's SDGs, where one of the goals is reducing inequality. Now, I gave you a model which explains why inequality is there, and I'll soon show you how to reduce the inequality. Along with that, I'll show you also my work related to the other goals of no poverty. So I was telling that one of the goals is reducing inequality. And so what we proposed was in 2000, a model where we said that, okay, if I consider the agents stuck in a room, like I explained, and each one of them are exchanging some amount of money, and then slowly you can show that and this model was called the Chakraborty model, 2000. It was published in European Physical Journal B. Now that we have completed 25 years, you will find a more recent review written by Max Greenberg and Oliver Gao, the 25 years of random asset model, where our model is also discussed. And we show that the distribution of inequality, there's these probability distributions of money, you'll have different types of money depending on how much you are saving. And we show that even if you start with the same amount of money, everybody having equal amount of money, you'll slowly go to a stable equilibrium where there will be inequality. So I will not go any further with that, but the physics behind them is similar to what we study in kinetic theory of gases, which you studied in school, that you have different randomly exchanging energy. And so what you get is a Maxwell-Boltzmann distribution. Now, this is something which we knew for more than 100 years. What we did is effectively map this to an economic model and showed that the effective dimension is D, and you have the same equipartition theorem as in classical physics. And then what the distribution you get is called the gamma distribution. The Maxwell-Boltzmann is a special case where D is equal to 3. And so what we did is a model analogy between the kinetic theory of gas and the economy, and we showed that you get the same type of distribution. Now, instead of saving propensity, which is the fraction of money you are saving, we can keep it constant for all the agents, or we can make it different for different agents. If I make it a different for different agents and draw it from a distribution called phi lambda, that means I don't all the saving propensities are different, and I'm drawing it randomly from a broad distribution. Then you can show that you will get, and that is what we call the Pareto law. And we published this paper in Physical Review Letters using what we call the variational principle. Now, Pareto power law is seen across the world in different types of societies. And here I have data from UK, US, Japan, and everywhere you'll find that tail happening. And there is a recent article by Thomas Piketty and others where they say that, see, some of the nations become rich at the expense of others, and which I was explaining is again like a zero-sum game. Now, Pareto law was discovered way back in 1896, 1897, where he showed that there will be always a tail and it goes like a power. So we have a book again published from Cambridge called The Econophysics of Income and Wealth Distributions, where we explain all this, and we show also with data analysis that if you incorporate savings and you encourage people to save, then the inequality, which is measured by the Gini index, it will go down. And so we have done some data science modeling, and I won't go into the details, but you can have a look at this paper. So as I showed that this is one of the goals of the UN SDGs. Similarly, another goal is building inclusive economy and to remove the poverty. So I want to point out this article written in 1910, and it's like more than 115 years ago, where they were trying to predict the price of corn from its productivity. So they were doing basically a linear regression model. Similarly, there was another article published in 1913 which talked about business cycles and production of these different crops and how their prices move. But even after 100 years or so, we could not predict, for example, the 2008 subprime crisis, when three of the biggest banks, Lehman Brothers, Merrill Lynch, AIG, crashed on September 15. And then you found that the effects of the crash, percolated amongst the other sectors of the economy and spread from the US to the other countries of the world. Now, we also had similar types of things way back. It used to be called the dot-com bubble, and then the bubble crashed. Or now you may have seen that month of April, after DeepSeek was introduced, there was on one single day, NVIDIA lost $600 billion. Now you will see that this type of disruptions happen, and we look at the market and we try to understand what is going on and how the markets would work. So, because here we have many interacting agents all trying to collectively find the best price. So what you'll see is the movement of price, yeah, and we try to analyze those prices and predict what is going on in the market. So typically what we do is, if you remember the thing I was showing also, the first person to model the prices was Louis Bachelier, who published a paper way back in 1900. And this was published in the Annales Scientifiques de l'École Normale Supérieure. He was a student of Henri Poincaré, the famous mathematical physicist, and he basically derived what we call now the random walk. And this was 5 years before we actually had the theory of Brownian motion by Albert Einstein. So this video you would know that when Robert Brown saw pollen grains in a fluid medium, water, in way back in the 19th century, the thing was explained, and it was published in Annals in Physics. And there is a nice article which talks about the journey from Robert Brown to Einstein's random walk theory. But what many physicists don't know is that the mathematician Louis Bachelier applied it to study the movement of prices in Paris Bourse. And what we typically study are sometimes not only the single price movements, but also pairs of stocks. So, for example, here I am showing that there are the stock prices of Pepsi and Coca-Cola going up and down since 1975. And you'll see that, okay, there is a high amount of correlation between the two. Yeah, you see this? So we can look at the correlation between the price movements of any two stocks or a group of stocks. For example, here I have all the stocks in May this year, all the stocks of the AI tech giants. Okay, so we can look at a specific sector like AI and then try to understand, is there a bubble or a crash coming? So these are the type of questions we ask. So like I told you, that we start with these correlations. And what we do is we look at, typically compute the correlations between two returns. And then I have here, for example, 194 cross 194 correlation matrices, which are evolving over time. And you'll see certain patterns which are more prevalent sometimes and less prevalent at other times. So this is the correlation +1, and this is the if they are anti-correlated, it is -1. And you will see that sometimes the entire market becomes highly correlated. But when I look at the evolution, like I was showing, you will see that the mean correlation fluctuates. And when you have very high correlation, these correspond to the well-known market crashes. So here we have Black Monday on October 19th, 1987. Here we have the Lehman Brothers crash, which was September 15, 2008. And then you will see that during these times, it's not only the returns which are falling, but or correlations which are rising. The volatility, that means how fluctuate the market fluctuates, that goes up and the risk goes up. So it's very risky to invest during this period. Now, these are what we call critical states in the language of physics. And you'll see that such type of things have been already studied in other physical systems. So there's a very nice article given by the group of Martin Scheffer, which was published in 2012 in Science, where they talk that across complex systems, it's not only true in financial market, but also in ecological systems, in environmental systems, in biological systems, in chemical systems, you will have these tipping points. And remember the slide I showed behavior. Yeah, I was talking about how the onset of sleep is also a tipping point. Now, we showed that during these times, you will have what we call at the time of stress, you will have high amount of connectivity and homogeneity, and in a normal time, it will have a modularity and heterogeneity. This we showed way back in 2003 in this article, where we showed that during a market crash, the topology of the network of the entire market changes, and you have high amount of connectivity and homogeneity. If you want to look, you can just check this paper and read more. Now, many of these complex systems also have other critical dynamics. So here, for example, on the left, I have the movement of S&P 500 index, and I have a log periodic oscillation. The same type of oscillations are also seen in earthquakes. And this was studied, for example, by Didier Sonnet, and he published a book in 2017. This is the second edition, Why Stock Markets Crash. Now, the laws which are present in earthquake dynamics, one you've already studied called the Gutenberg-Ritchie law. The other one, less known, is called Omori law, which means that there are aftershocks which follow shocks. That means if I have a big earthquake, I will have aftershocks. And there is a certain law which is known in the field of earthquakes. Similar type of law was shown by my colleagues Fabrizio Lillo and Rosario Mantegna, that in financial markets also, after you have a crash, there are aftershocks. And so they showed that, the financial markets and earthquake, these dynamics are similar in nature. Now, I have been working in this field from 2002, so it's more than 2 decades, and several articles. Here I will talk only of the last one, which we published with Indian stock market data. Now, if you're already, scratching your head that what does physics have to do with this, I will show you that, the same type of things that you studied in high school, which is the phase transitions. And in high school, you study between, 3 phases of water, ice, water, and water vapor. Same type of studies which we do in financial market, and we try to see, are there any phases? So there were 2 back-to-back articles written by the group of Jean-Philippe Bouchot and Professor Letters way back in 1999. And one is called the noise dissing of financial correlation matrices, and another one, universal and non-universal properties. And both of them had similar studies. Now, what we did is with the newer data, we have shown that you still have that similar type of properties. So if you look at the correlation matrix and you look at the eigenvalue distribution, you will see that the distribution looks like this. If I zoom out this first part, it looks more like this. And this is called the Marchenko-Pastur distribution in random matrix theory. Now, what you do is you use this random matrix theory to filter out the noise, and then you have information about the different types of groups or sectors. So typically, you take any correlation matrix, you can decompose it in different ways. One way is to look at what we call the market mode, the group modes, and then the random modes. So if you want to look at, we have a book chapter called Complex Market Dynamics in the light of random matrix theory. Now, here I show that as the correlation matrix changes, I can decompose the matrix and I'll see that the pattern changes. Now, from this correlation matrix, I construct what we call the entropy functional. And from a correlation matrix, I get an entropy H. From its market mode, I get HM. And from a group random mode, I get another entropy functional. And when I look at the market, and here I will show a video that as my market changes, my correlation matrix will change. So this is the timeline. And what is happening is that these entropies that I talked about, H, HM and HGR, they also change. And we constructed two HGR and looked at the absolute value. When I plot them, then I get that there is a phase separation. So you'll see that all the market crashes are marked in red, all the bubble formations are this blue, and you'll see that this dot, which is representing each of these market, it moves in different directions. So whenever there is a crash, it goes from here, the gray part, to the red, comes back to the green and back to the gray. And whenever there is a bubble, it goes from here to the blue, then goes to the deep blue and comes back. So we showed that in USA, for example, the Black Monday crash, it went like this. Or in the dot-com bubble, it went like this. And this is not only true for US, but it is true across different markets. This is USA, this is Japan, and we have done in other 5 countries also. What we see is that this type of phase separation is a universal feature. It doesn't depend on a single market. It is seen across markets. Now, I come to another technique, which is called the topological data analysis. And that's where we talk about the shape of data. So we tease the topologists, who like mathematicians, that they cannot distinguish between the coffee cup and a donut. Why? Because with continuous deformations, you can actually go from a coffee mug to a donut, or from a cow to a sphere. So to a topologist, the cow and the sphere would have the same properties there. So what we do is actually, there is a lovely article written in Scientific Reports extracting insights from the shape of complex data using topology. And the very basics what we use are called the simplicial complexes. So a point is a 0 simplex, a line is a 1 simplex, a triangle is a 2 simplex, this tetrahedron is a 3 simplex, and so forth and so on. And how the mathematicians characterize are what we call the Betti numbers. And so the different types of the disk, for example, has a Betti number beta 0, 1, and the rest 0. A circle is beta 0 is 1, beta 1 is 1, and the rest, and so on. So you can describe these different geometrical shapes in terms of these Betti numbers. And these are what we call the homological, features. So if I have a data point, for example, here I have 2 concentric circles, you can show that the H0 will have the barcodes like this. Here, if I have a circle with noise, so I cannot distinguish that there are 2 circles, then I'll see that the H0 barcodes will have a distribution like this. So typically what happens, if I have a data point, I start zooming into it and I look at different structures, these structures which I was showing, and I look at how much those structures persist. And that's called the persistence homology. So you will find wonderful tutorials in these sites, and you can show that as I zoom, I will see that certain features are two is for the financial market. We start with these correlation matrices. We construct these different data matrices, and then I look at the persistent homology between these. And with that, then we have studied in the Indian stock markets. You'll see that the market movements will cause the stock market index to fluctuate up and down. So here we focused only in this period, and you will see that the stock market movements are influenced by socio-economic and political activity. So if there is a disturbance or a war, then you will see market crashes. COVID pandemic, market crash. Then certain events which boosted the confidence of the market, there will be a rise, and those type of things. So we try to look at how the market evolves using these features of the topological data analysis, and we show using different features, what is happening in the market. So that is what I was saying, that I can actually look at the shape of data using these types of tools and techniques. Now, I wanted to go beyond just these financial markets and show how we use this type of tools also in other things. So agriculture is a very important thing for our country, because 75% of the economy is still agriculture based. And this is related to the zero hunger goal of the UN SDGs. So what you will see that in the last many years, there have been a lot of farmer protests going on. You would have remembered also that in Delhi, for many months, there were severe blockades at the boundary of the Delhi NCR, and people were protesting. And this is not only true in India, but in several other countries, the farmers have been protesting because there are several challenges which are faced by the farmers. One of the major challenges which we thought we could address is studying the price volatility. That means the fluctuations in the price. So the way we did is that we studied the prices for soybean in the state of Madhya Pradesh and the prices of brinjal in the state of Orissa. So this is from, for example, 2012 to 2025. End of 2024. So we see that the fluctuations are going up and down. From there, using models of econometrics, which we call the GARCH model. GARCH stands for Generalized Autoregressive Conditional Heteroscedastic Model. So this is what the economist Borislev and others got the Nobel Prize for. They introduced it in the period 86 to 88, where they tried to model the volatility using this autoregressive or multiplicative stochastic processes. So what we did is we looked at the analysis and we took the prices and the volatilities in different districts and then used statistical ways to find which are the hot. This type of insights can help the district administrators to actually control the price volatilities or secure better prices or secure the minimum support price or determine the minimum support price for the farmers. So we did this type of analysis for different crops in different states. Here we show only the soybean and brinjal, but we have done for other. So this paper was in the archive. It's actually under review in one of the journals, and you can see this article in the archive. The other one which we are looking at is from this price volatility, I can actually estimate the risk, and then to hedge the risk, we can introduce what we call the insurance premium. Just like you have life insurance, so you can also calculate what we call the crop volatility insurance so that the farmers do not have to suffer from huge losses. So this work is being done with Sejal, Abhinav, Manish, Ashok, and others. Now, last part, I have about a few minutes, I think. I'll talk about climate change, which is again related to the UN goals and goal number 13. That this type of modeling was started way back by the British polymath Richardson, and this is Sukuro Manabe in 1972, where he was actually giving physics-based models to, model climate processes. And we have now moved way ahead. But in spite of all these progresses, you'll see that every year we suffer from, heavy air pollution now in Delhi NCR. The air pollution is 350, 400 and above. It's not going down. And every year around this period, November and December, we have this problem. So we studied with one of our scholars, who is now a faculty in UPES, and we looked at the causal links between anthropogenic emissions and air pollution. So we studied, how temperature, PM 2.5, ground ozone, which is a pollutant, and we looked at the time series for many years and across different stations in the Delhi NCR. And then we tried to look at the correlations between them, and we modeled using machine learning. I am not going to show the details. And then we use these machine learning models to actually see what happens in the NCR hourly. And you'll see that what is very interesting is that PM 2.5 and ozone are both pollutants, but you try to control PM 2.5, ozone will go up. You try to control ozone, the PM 2.5 will go up. So they tried doing this in China. And then people realized, and we are showing and, we are pointing out that, yeah, that's correct, that if you control the pollutants like nitrogen dioxide, carbon monoxide, sulfur dioxide, which result as activities of human beings, either through the factories of or through the vehicles, and you control all these, then only you can control PM 2.5 and ozone. So we have several machine learning and data science models which you can use to show what is going on between these different pollutants. And if I want to control effectively, how I should things. So this is something which the policymakers can then use. The last 1 minute, I want to talk about also climate vulnerability. So you have models which is under the what we call the CMIT 6. 120 different countries make models for predicting what will the temperature, precipitation, humidity, and many other factors. And for every city, we can then analyze the data and show that this is now in 2024, but up to 25 100, what will be the scenario? And then you can look at how the different states will be vulnerable to climate change. So here we show from that period till 2100 than others, right? So I can actually again help the state governments to prepare for climate change, and again the policymakers can benefit from this. The last goal is health and well-being. Again, we are seeing that due to climate change, the number of heat waves are changing. And with some of my master's students and others, we are trying to model again that in the next few years, how will the climate change affect? And we'll see that the mortality, again, we are building machine learning models to the future scenario and what will happen in the future scenario. So you have two scenarios. If we take care and we have the moderate scenario, if we don't care about the nature or environment, then we have the worst case scenario. And in this case, I have two scenarios. One is called the SSP 2 4.5, which means shared socio-economic pathway, 2 4.5, which is the moderate scenario. And this is the worst case scenario. And you will see that the several states will get very badly affected by the deadly. Similarly, we're also working with mental health because it's again something which we saw specifically during the pandemic and after, that a lot of people get affected by this depression, mental disorder. So we are looking at EEG signals. This is Abhinav, this is Shrishti, Ingita, Cynthia, and we are looking at data from EEG, ECG, and galvanic skin response, so GSR, and we are trying to model using the similar tools and trying to understand what goes on in our brain. And so we also look at things like how does Indian raga, classical music, have effect on your brain? Does it calm or soothe it, or does it make more restless? Those type of things. And we find that there are certain ragas which can help in the mental well-being. So finally, I want to end with one slide. This is the work of Rishidev, who's about to submit his thesis. We are also looking at using tools of complex systems, bipartite networks, that each of these states are chasing different sustainable development goals, but all the goals are not easy to achieve. Some are more difficult, some are easier. So we've come up with what we call the GENEPI framework to look at how the Indian states are progressing and how are they achieving the different SDGs. And so this paper was published in the journal Evolutionary and Institutional Economics Review, which is run by the Japan Association for Evolutionary Economics. So if you are looking at how does complex systems and network science theory help in understanding institutional behavior or in evolutionary economics, I would ask you to read this paper. So the takeaway message is that we are looking at different systems, and I think I talked about all these systems, portfolio optimized neural networks in AI, or the economic complexity, which we used in this last, have similar types of optimization functions. And we try to find, the goal, our goal is to minimize these cost functions. And the similar type of maths and physics is behind all these different phenomena. So with last two or three slides, one is the highest education is that which does not merely give us information, but makes our life in harmony with all existence. This was, told by our Kavi Guru Rabindranath Tagore. And you will see that he implemented this in Vishwabharati University. And you'll see that the classrooms there have no doors and windows. So he wanted it that the knowledge should not be limited to classrooms, it should go out in the open. And he was way ahead of his time and used to think of entrepreneurial and sustainable means. Now, looking at that, we have a startup. We called it H new after the Planck's formula E equal to H new. And when I was the dean in Munjal, we started this startup which makes lithium-ion batteries and converts the diesel engines to electric vehicles. And this was Kumar Mangalam Birla and Sunil Kant Munjal. He's the CEO of Aditya Birla Group. He's the CEO of Hero Foundation. And they were here to inaugurate our startup. Similarly, I have another startup now with some of my colleagues, which we call Sharada Vidvat Foundation. And we have formed an institute for interdisciplinary research, which was launched in 29th November. And you can find the details in the website. And that's my contribution towards quality education, the graduates, postgraduates, and PhD scholars. And we are trying to work without any disciplinary boundaries. So we have social scientists, computer scientists, mathematicians, physicists, statisticians, all working together. And we also want people to come forward and come with their own ideas, have workshops and training programs. I also run what we call a Sunay Foundation, where we educate underprivileged children. And I'm the chairman of the trustee board. And we have many centers in Vasant Kunj, in Hardoi, in UP, in Darbhanga, in Jharkhand, and Kolkata in West Bengal. Again, a way of contributing to the quality education. I'm also a mentor at what we call the Sabud Education, where we train data scientists for free. But it's like a rigorous 6-month program, and you have to spend about 600 to 700 hours. And we try to bridge the gap of knowledge, what we teach you in the university and what the industry expects. So if you want to go to the industry, I would suggest you can work, and this is for free, except that it is a very rigorous program. I was also one of the founding members, what we call the Center for Complexity Economics, Applied Spirituality and Public Policy. We started it in 2020 in Jindal. But if you're wondering what does spirituality got to do, I end with this quote of James Gustav Speth, that I used to think that top environmental problems were biodiversity loss, ecosystem collapse, and climate change. I thought that 30 years ago, science could address these problems. I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with these, we need a cultural and spiritual transformation. And we scientists don't know how to do that. So for that, we also need to align ourselves with the goal number 17, which is partnership for the goals. So here is my Google Scholar page, and you can find all the papers there. I have written this book along with other co-authors. This is a textbook on econophysics, and these are 3 books from Cambridge University Press. I have many other edited books and volumes, but I'm not showing them. And finally, my hard work, I'm specially elected as a fellow of the World Academy of Science in the category of economics, social sciences, and humanities and arts. So it's like the recognition of the work that I've done in interdisciplinary field and how it has helped in economics. So this is my webpage and email ID. Thank you very much for your attention. I think I overshot by a few minutes, right?
Yeah. No, it's okay. So thank you, Professor Chakraborty, for a wonderful talk. So I think now we can take some questions. Anyone? So Professor Shubhan, do you need to unmute people, or which way you want to take the questions?
Or you can tell them to write it on the chat box if they want.
So if anyone has question, you can write in the chat box.
I can see some comments.
Yeah, I think you can see it. Yeah. So somebody wrote, so I have a question that in economy, if you can't have equality, but can have a continuous rotation happen where rich remain rich and poor become rich? Example like how Apple replaced BlackBerry with coming new better products.
One is in the field of what we call business cycle or innovation cycle. So you will see often that there will be ups and downs. And as new products come or new businesses come, often the old ones are displaced or disrupted. And so you will see often, like you've rightly pointed out, that if you are not willing to adapt, then some of these technologies become obsolete or die and new technologies come back. And this is what they teach you in management schools or business strategies, that how you must adapt with the market. Now, three very famous examples of decline is one is Kodak because they didn't adapt to digital photography. The other one is, for example, Xerox. They didn't adapt and introduce digital printing. And the third is, for example, Nokia and BlackBerry. They didn't adapt so quickly to smart phone technology and other things like Apple and Samsung did. But what you are asking is also probably that within the economy, suppose I'm a rich guy, can I become poor and another poor person become rich? There are several factors. Here, I was only looking at, for example, how saving propensity helps you to reduce the inequality in the society. But how an individual will win or lose depends on a lot of other things. So we can't give a theory from sort of econophysics that what would help you to become rich. There are several factors which are known, and that economists will tell you better. Any other questions?
Anyone has any other question?
Nabindu, I have one question.
Yeah, please ask Rakesh.
First of all, thanks for a very interesting talk. This is related to your discussion regarding this oligarchy that you had. So I don't know whether I missed it or you didn't go into the details that much. I know. So can you point out what is the main reason, if if it is possible to do it in short time? What is the main reason why only a couple of people will end up becoming rich? So what is the key element that is responsible for that?
So what we show is, for example, if I even do the trade with the coin toss. Okay, so every time I get head, I suppose win. Every time I have a tail, I lose, and I give up a little amount of money, or I gain a little bit. But if I have unbiased coin, it is one thing. But if I have a biased coin, which can show that, then you will see that the wealth will flow in one direction, and only a few will win. So I can point out these articles. They were following my paper in 2002. Professor Bruce Bogosian has written several articles, including in the Science Journal of Mathematics. So if you want, I can just point it out to you and it'll explain why it happens like that. Why are the oligarchies there? But what I was showing is that with this simple kinetic exchange type of models, you can explain this oligarchy formation, and which is not desirable for the society. But then you can tweak the rules of exchange, and as we showed that in the Chakraborty or CC model, that if I introduce savings, then you can reduce the inequality. If I introduce taxes, maybe something else happens. If I allow people to borrow or have thing from the banks, then again something will happen. So then the real economy is much more complex, but you can study using this type of framework how the real economy works.
Okay. Okay. Yeah. Thanks a lot.
I see one more. Thank you, Professor. And I see one more question by Narendra Kumar. He says, could you talk a little about how easy or challenging your transition from physics to economics was? Oh, okay. So as I told you, in terms of knowledge, it was not a very difficult thing to do because the training in physics actually helps you, and you can pick up many other concepts and techniques in economics quite easily. What people often don't hear about is that there has been a exchange of ideas between economics and physics for very long. In fact, Adam Smith, who's known as the modern father of modern economics, he introduced the idea of self-organization. That means the society or market acts in such a way, it's a self-organizing system. And that's why you can explain all these business cycles I was talking about through this idea of self-organization. For example, now we have a AI booming. I'm sure that is the case in LNMIIT also. And people will not go to traditional physics or mathematics schools, but they'll go to only the computer science engineering. Now, what happens is you produce huge number of computer science engineers, and perhaps more than what the market requires. So then what will happen? There will be more supply than demand, and then there will be many people who will become unemployed. And when you will see that the number of jobs are going down, then less students will opt for computer science. And so you will see that this cycle goes. Okay. Now, what I was telling is that one is in terms of knowledge, the idea. So this idea of self-organization was also a thing found in physics. We called it self-organized criticality, the sandpile model, which was introduced by Per Bach, Tao Tang, and Kurt Wiesenfeld. And we study self-organized criticality. Like if you have a pile of sand, and you're throwing sand, you will see that it will maintain a slope. So there are no other forces except the force of gravity, but the sand self-organizes to maintain a critical slope. Now, this type of ideas have been rolling back and forth, and not many people know that Jan Tinbergen, who was the first Nobel laureate in economics, was a student and a PhD in physics. He worked with Paul Ehrenfest, and he did a PhD in physics. Similarly, Paul Samuelson, who's also a Nobel laureate in economics, borrowed the idea of Hamiltonian mechanics or Hamiltonian dynamics into economics, and then formulated what we call the maximization of utility principles and others. So there has been sort of flow of ideas from physics to economics to physics and all that. So in terms of knowledge exchange, it's not a challenge. The challenge was like what I was telling, that when I was doing physics, it's economics. And the economists would say, no, this is not economics, this is physics. Then to get the attention of both, or to establish myself as a scientist, was more of a challenge. But I think now people have started accepting that, this interdisciplinary approach helps people a lot. And you can solve, or at least approach, many of these problems with this economic physics approach here. I hope I was able to answer your question.
I think there is one more question.
Yes, one is by Ankita. It says that share the name of the book you showed us. Few slides, one again. I think this whole thing will be recorded and will be in YouTube, right? So they can have a look at the YouTube recording.
Yes. It would be in our archive, so student or a participant would be able to see.
Right, and you can look at the references also, or you can go to my Google Scholar page as I was showing, or even in this class page, and you will find all the details of the books and the thing. I think you were talking about the book written by Doyne Farmer. That's called Making Sense of Chaos. Yeah. There's one more question.
Okay, so yeah, there's a question by Avid Mustaq that are there any open source tools you recommend for exploring the shape of data?
There are open source tools, like even there are lots of very interesting papers on topological data analysis. And what I know, for example, this famous mathematician who was very successful in creating a hedge fund company, which is called Renaissance. I think, what's his name? Jim Robinson or something. He died a few months ago actually, but he employs these tools, TDA, into what we call algorithmic trading. So what happens is nowadays, most of the trading is done through computers. It's called algorithmic trading, and huge amount of computation needs to be done. So it's actually very difficult for individuals like us to compete with the big banks or hedge funds, and they use all these powerful computational tools to gain insights about the market, and then devise strategies to, sort of in their favor. See, you have to remember two things. One is gaining insight is one thing. So as a scientist, I'm doing that. But making money is another thing. That's where the strategy comes. So if I have the information, you must use that information well to build a strategy will help you to it. So when a market crashes, not everybody becomes poor. Most of the people will lose money, but a few who use it well can become super rich. That's what we saw during the pandemic also. That there were certain sectors, certain companies which made a huge amount of money. Why? Because they actually adapted and did something which helped them to come up with new products, healthcare industry, AI tech industry, because we all went to online teaching or modes of communication. These companies did very well. Pharmaceutical sector did very well, whereas the tourist sector was very badly hit. So the economy is very complex system. That's what I'm saying. And many of these tools can help you to study. We have papers where we have actually studied shock diffusion. So if I introduce a shock in the economy, how does it propagate in the entire economy? So we can use these tools like network science and other things to see such things, or what we call volatility spillovers. These are very important topics for economists, that if I have a fluctuation in one sector, how does it affect the fluctuations in other sectors? Okay, so you can use all these type of tools, and there are all these are open source tools actually. Yeah, if you want, you can send me an email and I'll send you more material.
Okay, so as I see, I think there is no more question, and in that case, I will thank you again and for accepting our invitation. And it was wonderful to meet you, even if it is online after a long time. And hope sometime we'll be able to invite you to our campus. And I hope you will accept our invitation again.
Oh, sure, absolutely. It was a
Yeah,
pleasure interacting with you all, and I hope to visit you all in person someday. Thank
yeah,
you.
yeah,
Right.
yeah, yeah.
Thank you
Thank
very
you.
much.
Mm.
Yeah.
Thank you all. Thank you all for your participation.